Okay, good afternoon, everybody. So one quick announcement. We're now at the end of week 2. We've now hit 2 Fridays right now. All of your, at least health-focused, New Year's resolutions should be done and dead by now, hopefully. Let's all just accept that. Today is our Canvas first quiz will open tomorrow. So that'll open up in the afternoon. You will have until 5 p.m. next Friday to do this. Remember, the rules of engagement this. When you open it up, you have infinite time. You have 3 attempts. We will take your highest attempt. So do start it at some point. I highly advise do not start it at 4 o'clock next Friday. If you have 3 attempts, don't just bang through all 3, 1, 2, 3 rapid fire. If you go through it, make mistakes, stop, contemplate the mistakes, think about it, try again. So don't just rush through all 3. Also, that will auto-submit at 5 p.m. So if you do start and you let it go open like that point, please make sure you submit it prior to that one. Don't let the time count down at that part. So last class, we talked about our ketones, aldehydes. This is where we're introducing our imines and our enamines, right? These are our primary and secondary components. Generally, we were talking about these is now we've gone through this process of starting from a carbonyl compound, oxygen nucleophile. That's sort of number 1. That gives us our acetals, hemiacetals, ketals, hemiketals. Imines, this is our nitrogen nucleophile. This is where we're making carbon double oxygen becomes carbon double nitrogen. That's swapped between the 2. The weird one, enamines, are just because we don't have this extra proton on nitrogen. We can't form another carbon double bonded nitrogen. We'd have 4 bonds to that, leaves a positive charge. We need this alpha center to help get to a final uncharged molecule. So now that you've talked through things like reactivity, different components, how might you do this? How might we go from that molecule on the left, molecule on the right? What's the process? So this one too, I want you to actually start out and discuss this one down. What's your strategy? How might you go this reaction? How do you control this one? And what are the problems you think you identify right now? Okay, time. So give me your thoughts. If I'm going from the molecule on the right to the molecule on the left, I at least need one other molecule added to this mix. What do I need? What reagent do I have to add over here to make this possible?
You need to add a primary amine, but before that you need to make a vector.
Okay, so 2 parts. Molecule, I'm missing this fragment. That's the thing that's different. Right? So let's just add that part in. And you're right, that's probably going to come from a primary amine. Right? So that's the constituent that I'm missing from this point. I don't know where. This could be part of a multi-step sequence. Catalyst. What do I need if I was just going to do this one directly? Let's say I'm only going to add that primary amine to this molecule. What conditions do I need for that one? pH 6, light acid, right? I need a gentle acid catalyst. So I could say something like protons. And yeah, that's our pH equals 6. Well, call it 4 to 6, right? Slightly acidic. Those are the general conditions, right? Okay, complication. If I just jam those 2 things together, will I get that product? You're saying no. Why not? What's the reason why? Not you. Give me somebody else. Yes? Right, you have 2 carbonyls, right? I have an aldehyde, I have a ketone. Aldehydes are more reactive than ketones. If I just mix these 2 things together straight up, I would expect to make the imine there, not on the ketone, right? So there's an order of reactivity problem here. The direct approach will not work. Okay, so what's my strategy? What do I do to get around that problem? 2 letters, yes. Protecting it with a diol. Now give me an example. Yep. Yeah, diol, maybe something like that, right? Something where you've got the ability to make a cyclic diol. This is our protecting group strategy. We're making an acetal would be our goal, right? So what I could do as step 1, I would use a gentle acid. So there's something like maybe acetic acid, HOAC. As my catalyst, I'm going to use this one. And I could make selectively, pretty selectively, maybe this, right? Now, the goal I'm doing here is I'm taking the advantage of the higher reactivity aldehyde that targets what's called the chemo selectivity, which group I'm doing. So aldehyde over ketone matches what we're looking for. Great. How would I get, like, could I make an acid, or like a ketal as well? Like, is that chemically viable? Can I take that diol and a ketone to make a protected ketal? Yes or no? How might I exert that control in this case? So it's possible, right? If I could potentially hit the other one, what's the only thing available to me to say I'm going to hit only the aldehyde and not the aldehyde and the ketone? You're right, aldehyde's always going to go first, but how do I prevent it from going twice?
Limiting the amount you add.
Measurement, right? You can only add enough of the diol. You would try to do this by giving it just enough, single equivalent, right? That's your only real enforcement of control. Totally true. Yep. Okay, now we've protected one. So now you guys are free to go and do acid. I'm going to take my amine, right? That looks good. Now we're set up to have my imine formation. And I would still have my protected acetal. All right, almost home free. How do I get to my product from here? What do I need to do to deprotect the system? Okay, so TFA, some acid, right? Acid catalyst. Water, why do I need water? It's your hydrolyzing, you're aiming to hydrolyze your acetal group, right? This won't work. Oh. What's wrong? Say it louder. Yes, you are going to hydrolyze the imine as well. Remember, how do you form an imine? We take a primary amine, we take a ketone, we take an acid catalyst, I condense it to eliminate water. That's how I made the imine to begin with, right? The other thing going in this direction is a molecule of water, which I have to remove from the system to make my imine. And then you're like, cool, now I'm going to take care of that acetal. No big deal, I'm just going to take this thing out and old Yeller style, everybody dies. The quick answer is, you can't. You guys do not have the skills, tools. You cannot do this reaction. The point I'm trying to work through with this one is that looks like oh, I see the reactivity. That's all great. Protecting it. Great answer. You know aldehyde over ketone. That last step, the step that you need to hydrolyze your acetal, is exactly the same step you would have to hydrolyze your imine. You have no way to do this right now, and that is totally fine, and I am sorry. Yes? What's that? Activate what, sorry, with SOCl2? Okay, yeah, no problem. But yeah, the quick part is, you're right. In order to hydrolyze my acetal, I must add water and acid back in. To hydrolyze the imine, that is exactly the same conditions. This is only meant to be a lesson that life isn't fair, but also that, remember, just because it feels good as you're sort of walking it through, stop, look at your conditions. There may be something else you're not seeing. The quick answer is there isn't a way yet for you to do this. We'll come back to that. Easier one. You guys remember these? Yes, sorry.
Are we able to use the same acid throughout the entire process, or should we switch it?
oh, like could you use the same acid for the addition, the same acid for this one, same acid here? Yes. In fact, in an advanced way, if you really, really wanted to do exactly this, the strength of your acid is probably the only handle you have to get any kind of selectivity in this system. But yes, you could just brute force. I'm using just TFA the whole way through. That would work. Yep. Yep.
So why couldn't you possibly form the tautomer with the enamine, then hydrolyze your carbonyl, and then form other like undo the tautomer and then hydrolyze?
Okay, hold on. I think what you're saying, I am going to make an enamine up here, like that. Is that what you mean?
Yeah.
Sorry, hold on. Let me redraw that cleanly. That's what you made. Now what? What's your move?
Then you could hydrolyze the
Try to hydrolyze the acetal? In order for that to, I love where you're thinking. In order for this to work, the enamine needs to be less acid or water sensitive than the acetal, right? Enamine is about the same thing as an imine, honestly. But it's a good move, good idea. Like you're adding like a double protecting group in something. Problem is they have very similar reactivities. The enamine is basically like a nucleophile. If you gave it protons, it will protonate very quickly at this site, and then you're back to an aminium, and then you're back to a carbonyl. But I love where you're thinking on that point. But unfortunately, same trap. There's one other thing too, just in terms of strategy I want to bring up. So what you just said is, oh man, acetal's more reactive. Okay, I'll catch it. Oh wow, and I got a carbonyl over there. Okay, well, I'll catch that one. And now I'm going to hydrolyze this one. Okay, that's more reactive now. What's your next move, even if it worked? Like, let's say that worked out, some strategy. Let's say I could open up my acetal back to the aldehyde. Now how do you switch the enamine back to an imine? Now you've created, and this is just a strategy for when you're doing questions. If you start walking through and you get to a point that's like, and now I'm going to divide by 0, stop and back up. You've created something way difficult. So that's 2 levels deep. Yeah?
Can you reduce the ketone here and then activate with acetate?
That's how you could do it. Exactly. The whole point is there's no way to do this simple condensation because of commonality. We're going to have to do some kind of reduction and oxidation chemistry on top of this to do this. This is where we got to go back and use something else.
Wait, so I feel like reduced it to the OH and then brought it back.
Maybe. Yeah, exactly. We're going to have to do some kind of manipulation along the redox scale in order for this to work. Yeah, exactly. Okay. This is the feel-good one after I beat you guys up. You can all do this. If you assign these as E and Z or neither, do you guys remember this? This is CIP rules for diastereomers of alkenes. Okay. Let's take them one by one. This one here. E or Z? Everybody says Z because why? The high priority groups are on the same side, right? This is a CIP, which means, remember, you need to be able to assign by CIP the scoring of these. Remember, what does CIP, like how do I give, you want to tell your mom or your brother about this? In your own words, what is CIP? How do I use CIP? Does CIP tell you about steric bulk, size? Not really, not always. CIP is the priority ranking based on the atom, based on the atomic number, right? I can have oxygen win out over a T-butyl group. Why? Because carbon versus oxygen might be the comparison I'm making. CIP is a formal, rule-based way based on the atomic numbers in a chain, not necessarily based on physical size. They are not exactly the same thing. If I had to call this molecule cis or trans, what would you call it? Cis or trans? So cis, trans. Why? Why trans? This is the problem. The naming cis and trans is a relative naming, but you have to sort of define what you're saying. It's kind of like saying, it's the ER ending. I was going to come up with something, I'm not going to say what I was thinking. T-butyl is cis to isopropyl. As long as I have two individual groups that I'm saying A and B, it is a relative marker. T-butyl is trans to ethyl, right? This is where it's a thing for close and far, near and it's a relative orientation that needs a binary comparison between two sites. Okay, next one, E or Z? E, right? The priority groups, high priority is fluorine, high priority is phenyl. But in terms of cis or trans, and again, let's talk about it in terms of the bulkiest or largest groups. Are the bulky or large groups cis to each other in this molecule? Yeah. So this is where E, you might call this an E and then cis molecule if you're talking about these two groups. But the problem is I'm trying to conflate those two. Cis and trans is usually a binary comparison to two parts. Usually for molecules like this, sterics is what we're talking about, big with big. If you're talking about E and Z, that's CIP rules. That's based on the number or the atomic number of our molecules. So today we're going to talk about olefination reactions. So we've gone from carbon double oxygen, carbon double nitrogen, now to carbon double carbon, right? So we're replacing the reactions we've done before where we're making carbon-carbon double bonds using what's called the Wittig reaction and the Horner-Wadsworth-Emmons reactions, or HWE. These are two different chemistries we can use. We are going to be making E or Z alkenes. We're going to be using nucleophiles, where the carbon nucleophile we're using here are going to be these guys, what we call triphenylphosphorus ilids. And what we mean by that is an ilid is a molecule that has a stable Zwitter electric compound. Usually ilids mean negative and positive charge, one bond away from each other. The phosphonate is the other one where this is my nucleophilic center. So both of them, what makes them common? They're both phosphorus reagents. They both have a nucleophilic carbon center. They do two different things. This first guy, guys like this, what we call unstabilized ilids, highly reactive ilids. These are our Wittig type reagents. These guys. These ones, where you have these phosphorus oxide with a stabilizing group here, these ones are my HWE reagents. The bottom one is different because if you look at that one, the carbon, blue carbon I've highlighted in the middle, you have stabilization on either side. You have two carbonyls, part of my nucleophile, which help to stabilize the charge on the nucleophile. Again, the specific thing I'm emphasizing here, Wittig reagents, typically the nucleophile is unstabilized, still has a phosphorus. HWE reagents, the nucleophile is stabilized. There's groups or delocalization adjacent to the nucleophilic center, which helps to make them less reactive. That's important because that's how the mechanism works. You get two different kinds of products from this one. So overall, we're going to be making carbon-carbon bonds. These are our olefins. Up until now, you've done some reactions like this, but if you think back, how else, back into your previous course, how else did you make carbon-carbon bonds? What's that? Elimination reactions, yeah, what else? Yeah, usually you take a molecule, you do a Grignard reaction to leave an alcohol, then you do an elimination. Something like that might be possible. But you have to set yourself up for eliminations. This is on that way. These reactions are like all of that, nucleophilic addition and elimination all in one bucket at one time. The reagent's been set up to allow you to do all of those steps in one step at one time. So both adding a new carbon-carbon bond and eliminating something to reform your carbon-carbon double bond, right? So two steps. In the end, what that means is, and this is why it's in this chapter, you start off with aldehydes or ketones, and you're going to get your new carbon-carbon bond. The geometry is the thing we're going to focus on here. The two different reagents, Wittig or not, gives you usually kind of two different geometries that are possible. Wittig typically, as we're going to show up now, depending on the reagents you want, Wittig reactions will typically start like this. You're starting with these phosphonium, or this phosphorus, excuse me, ylids. Usually we're using triphenylphosphine as the phosphorus component. Now if you notice this, we draw them as this stabilized negative positive charge. Normally if I drew the resonance structure of this, I could draw this as carbon-carbon double bond to phosphorus that way, because right, it's just taking that, right? It's kind of like what we've shown before, these one bond resonance structures. But remember, phosphorus already has 3 groups. So that means this has phenyl, phenyl, phenyl. So shorthand notation, circle thing, that's phi. That is a shorthand quick notation for pH, phenyl, or an aromatic group. What's weird about that phosphorus? Are we obeying octet?
It's hypervalent.
Yeah. Remember, you can get, this is where we lied to you about octet being a real thing. Yeah, it's not a real thing. As soon as you start going down, okay, for first row, absolutely. Carbon, oxygen, octet, right? Second row, now you have d orbitals, you have expanded octet, that's possible. This is a correct way, this bonding here, this expanded octet, you can draw it that way, that's correct. The way that we like to focus on this in this form, these are just, remember, resonant structures of each other, because it allows you to focus and see where the carbon negative is. It allows you to point and say, that is my center of nucleophilic of carbon. When you're like this, the more stable sort of isoelectric version, it's still there, it's just hidden away, you don't see it as obvious. So that's why there's some preference to show this in this way. How you make them? If you're building an actual Wittig reagent, you start off with usually alkyl halides or bromides. You do an SN2 reaction where I take triphenylphosphine. It's this lone pair here acting as my nucleophile, and that makes this salt. What I've done is I've done a displacement reaction where I'm using the lone pair to displace an iodide or a bromide. After that, I have 2 protons adjacent here. If I have this positive charge and a proton, what that's going to do is generally stabilize a negative charge on that center. What I just did is I took the protons that were originally adjacent to my alkyl halide, I've made them more acidic. By doing that nucleophilic addition and adding this positive charge in the phosphorus, now it's a lot easier to rip off this proton. Again, back to pKa's. Does anybody remember, if I take methane and I'm going to rip a proton off of methane, what's the pK of a simple, normal alkane? Stupid high, right? Very, very hard. Does anybody remember the pKa, like Bewley or LDA? Remember those bases? Those are pretty bad bases, but are they as high as 50? No, they can't deprotonate my normal starting material. But after doing this, now they can. We still have to go to something like Bewley, very strong bases. But these are now basic enough that butyllithium can deprotonate that center. So what that does is it leaves behind this negative charge. This is now my Wittig reagent. So every Wittig reagent is going to be formed by first a nucleophilic addition, then a deprotonation. You've got to use a base. And it's going to be a pretty strong base still. Yeah? It is more stable. Okay, this is where ER. It is more stable than that, right? You've gone down in energy because you're going from a positively charged only species to at least zwitterionic, right? That's one. Relative to all negatively charged species, O minus, fluorine minus, it's still pretty up there. Generally, and again, as a comparison, this Wittig reagent is a less stable, very reactive nucleophile when compared to the HWE reagents. Those are more stable nucleophiles. But again, I'm comparing a carbon negative versus a carbon negative species. So in that world, I am a carbon negative versus I'm a carbon negative. Wittig is more reactive than the HWE carbon negative species. That's the part, right? Yes? If I ask you, please go and make it, if this was a synthesis problem and I gave you only the alkyl halide starting materials, yes, you must build it. If it was just do the mechanism and I gave you this part as it is, you can start from there. It depends on what you've got in the question. Yeah?
We have to also build like the lithium.
You'd need to bring it to the party, yes. So again, if I gave you only the aryl halide starting material and said, you can do anything you want. Give me an alkene at the end. You need each of these steps to prep your material, for sure. Think of this kind of like a protecting group strategy. You're getting ready for the reaction by building the reagents you need first. Any other questions? Great questions, though, guys. Okay. Now that we've got this nucleophile, we're going to make a double bond. For Wittig, the most important things, a Wittig reaction will generally put the two bulky groups on the same side of the alkene. That's not E or Z necessarily. That is cis to each other. The two bulky groups will typically be on the same side of the alkene. Now again, if you started with an aldehyde, and a lot of the time we start with simple monofunctional compounds, these will build Z alkenes. That is, and remember, that's only really true if you're talking, I start from an aldehyde that's a carbon versus a hydrogen, and I start from a single monofunctional Wittig where I only have, H and H from two different sides. That's that transition of, Wittigs make Z alkenes. No, the general rule is bulky goes with bulky, right? That's the part. So there's these kind of two layers you have to move through. Yes? Abbreviation for PPH3? Unfortunately, no. Like the best you can do is you have to draw this. It's the same thing as like NH3, right? You can either draw it out as P and then phenyl 3, or like I said, P phi 3 if you like. Those are both sort of equivalent. Make sense? All right, now look at the overall pieces here. The molecule you're making, if we map out the atoms, that carbon is this carbon. This carbon is that carbon. That's where those two pieces came in. Now look at the rest of the structure. The phosphorus piece ends up departing here, and the oxygen departs here. This is what we would call like a metathesis reaction. So we've talked about substitution, elimination. We might bin this in what's called metathesis because what you're doing is two double bonds this way become two double bonds this way. You guys old enough for Vogue? No, you're not. It's okay. Madonna was a thing years ago. Look it up on the internet. It's great. It's a great joke. You just don't know it. But what I'm saying is you have four partners, right? I have pink, green, blue, red, and I'm changing which partners we have. Overall, the bond content here, two double bonding compounds become two different double bonding compounds. I'm switching a carbon-oxygen double bond and effectively a carbon-phosphorus double bond for a carbon-carbon double bond and a phosphorus-oxygen double bond. Right? This is an overall part. So keep that in mind because that's the inventory of reactions you have to have. There's going to be a nucleophilic addition, some kind of sigma bonds, and then some kind of elimination reaction to make this all happen. All right, let's go. The mechanism looks kind of like this. We start off with the nucleophilic center is attacking this group. So at least from the arrows, not too bad. We've got an R group. I've got an oxygen that picks up the negative charge. I've got a new bond where I'm going to draw the hydrogen over here. And then on the other side, I'm going to have my R prime, my P, PH3. That's still positively charged. So I went from an ylide, which is a zwitterion, to this guy, which we would call a, does anybody know the name of this? The Germans did all this work, so I'm sorry. We call this a betaine. I don't know why. There was this whole, again, this is not that super important. I'm giving you this for trivia. If you see this in other points, these are where the namings are. Wittig was the name given to a zwitterionic compound where the carbon and the charge were one bond away. Betaine is the name they gave to things that are 3-4 bonds away, but it's still just a zwitterionic compound. All we've done is do this charge-separated species. Now, what's interesting about this, though, is once I'm set up like that, I have a negative center, I have a positive center. I can rearrange this by a bond rotation here to orient them so they're actually closer together. So let me redraw this where I've got my oxygen. I'm going to draw this where my R group is sticking out like this. So if this here was the R group was sticking out, whoops, and let's say the hydrogen was going back, I'm going to do the other thing on the other side where, let's say initially this R group is going back and the hydrogen is sticking forward. That's where the oxygen is up, phosphorus is down. It's more like that sort of sawhorse type structure when we're like this. We've gone from 2 pi bond systems to the sp3. When I do that bond rotation, what I've now done is I've taken this R prime that was in the back, and it's going to be up front here. The phosphorus is going to swing around and do pH3. And then that means this hydrogen that was in the front will be tucked in the back now like that. The reason I'm doing that is it allows me to take my 2 charges and I associate them together. I'm basically putting them close together to each other by Coulombic attraction. Oxygen finds phosphorus. Yes? That's the key. It was a carbonyl group. It's not a carbonyl group anymore. So does the stereochemistry matter? So, yes, it does. Let me show you just in a second. Does everybody, okay, I want you guys to be comfortable with this. I chose one face where this group, this is a flat group, right? Starts off as a carbonyl, flat group. So I need everybody here to walk along. This is what we call olefination patty cake. Left hand. Everybody left hand up. This is your carbonyl. The heel of your carbonyl, that's your carbon. Your fingers are your oxygen. Your thumb is your R group, okay? So if you look on the plane, this is what you should all have, right? Like if you see what's up on the screen, that lines up. Everybody agree? Okay. Other hand, right hand, this is your illid. Again, palm of your illid, that's the carbon. Fingers, that's the phosphorus. This is your pi bond, right? Carbon phosphorus pi bond. Thumb starts out like that. That's kind of what I got drawn over like this. These are 2 flat molecules that can be combined in 4 different ways. 1, 2, 3, 4. Yeah, I've done this a couple times. All right, what I mean is palm to palm, right? Palm to back of hand. Flip both of them, back to palm and back to back. Ow, right? That's if my fingers are both aligned. Your fingers, carbon, oxygen, left hand, that's a dipole pointing towards your oxygen. Phosphorus, carbon, it's a dipole the other way. The way that this first approach happens, your heel of your left, your heel of your right will come together so your fingers are opposite each other. What that does is it takes the carbon-phosphorus bond and the carbon-oxygen bonds and it orients them 180 degrees to each other. That's number 1, right? So what I'm telling you is, number 1, the only way these groups approach will now be 1, 2, 3, 4. Your fingers have to be opposite each other, so you're not doing this anymore. You're only doing this. Now look at what happens with my thumbs. If I go, so again, fingers opposite, palm to palm, what happens? How are your thumbs doing to each other? Good puppet show, right? They're away from each other, right? If I flip both of them back to back, what happens to my thumbs? They're away from each other. Is that low energy? Yeah, because the bulky groups are away from each other. So this and this are cool. So in the final exam, I want to see a lot of this. But what happens is, so those are enantiomers to each other. They're mirror images. But your fingers are actually opposite. What if I do this? What happens now if I go palm to back or back to palm? Your thumbs they're bumping into each other. So of those 2, palm to palm or back to palm, which one do you think is lowest energy? Palm to palm, right? Or back to back. Those are enantiomers, but palm to palm wins, right? Okay, but we just said your phosphorus, right hand, and your oxygen, left hand, are now opposite. But they have to find each other because they're coulombic. So you rotate. What happened to your thumbs? Yeah, this is called a trap. Your first intermediate that you form, that betaine, will form the more stable intermediate where the two R groups are away from each other. That is number one. But if you have to go through the elimination, you just put the two R groups on the same side as each other. That is why the Wittig reaction makes two R groups. Oh, I know that face right there. That's why I do this. What you just did was this. I start off with the two R groups opposite, front and back. I rotate it front and front, and they end up on the same side as each other. This is only possible if this first addition is fast, that's why I'm doing it, and irreversible, which means it has to be a very high energy nucleophile. If this is stabilized, I can try other things because this, again, we'll get into that mechanism next. But that's why you get this, is the first attack is the one that determines the stereochemistry. After that, for the elimination, you're stuck. So this is the same thing as, oh, when I was young, I told him I'm going to be an artist. That's a bad decision later in life. I'm sorry. Okay, while you were young, you're going to be a biochemist, and then it's a bad decision later in life. So again, I've shown you the geometries of what this looks like. For the purpose of time, let me switch over to this, because I've actually, so somebody that helps me out this class, her name, I wish you guys ever got taught for her. Her name is Erin Lindenberg. She is a phenomenal educator. Let me show you this. She found this one. Here is a video that I will post up online. Oh, come on. You can do this. That's not it. Hold on. Bloop. And okay, so take a look. This is the movie of this whole process, SN2. Then the base comes along. You've got an ylid. The ylid finds the point, lines up, nucleophilic attack, swings around, takes the thing, does the elimination. Ta-da! So helpful, right? Okay. I'll post that part back up online so you guys can see it. But this is why you get this enforced geometry. It's this specific point of the opposite attack, followed by that rotation, followed by that elimination. That's how the sequence actually works through, right? The arrows for that elimination looks just like this. What you're doing is a nucleophilic attack makes your betaine. They associate with each other. What you're doing is you're breaking the carbon-phosphorus bond to make a double bond, and you're breaking the carbon-oxygen bond to make a phosphorus-oxygen bond. So that's where the second bond formation happens here. One of them is just the Coulombic assumption between the oxygen and phosphorus. The pi bond is through the elimination step. And that's the same thing here. Carbon-carbon bond, the first one forms through that first nucleophilic attack. The pi bond is this elimination step we've got shown here. So that's the overall arrows of this process. And again, like I said, there's the video. So I've got a couple follow-on questions. We're going to do those ones online. I want you guys to do this part later, and I will do that part at the end of the video. The last thing I want to talk about, though, is everything I talked about, remember, and I want you guys to really, really nail this one in. Wittig reactions use what we call unstabilized ylids. They are a carbon negative with just triphenylphosphine. There's no resonance stabilization. The negative charge really only has that phosphorus plus to deal with, but there's no other added help or assistance. Yes? Pretty much. Like, again, if you wanted to get really fancy, you might use dibenzyl monophenyl, but it's going to be a triaryl phosphine or a trialkyl phosphine of some kind. It's phosphorus with 3 other groups on it, lone pair. And again, the molecule, both the bromide you start off with and the triphenylphosphine, has no other special stabilization associated. The HWE groups are slightly different. They still have phosphorus in them. We still have a phosphorus. They're usually what we call phosphonates. Instead of being a trivalent phosphorus, they're now the pentavalent phosphorus. These are P double bonded O already baked into them. So this is kind of the part that instead of triphenylphosphine, you've got these phosphonate compounds. More importantly, though, each of the HWE reagents on the nucleophile has some kind of group with some kind of resonance stabilization. You've got a cyanide next to the carbon minus. You've got a carbonyl next to that. You've got a sulfonate next to that. So really what makes these guys different is this nucleophile has a lot of help to spread that charge out and delocalize it, which makes it more stable. That's the key. So being able to look at your reagent and say, which kind of nucleophile is this? An unstabilized nucleophile. Wittig, bulky groups go on the same side. If it is a stabilized nucleophile, phosphorus has this extra pi bond. There's another pi bond on the other side. That is an HWE reagent. The way you make them is actually kind of simple. You start off with these guys, where you've got usually 2 pi bonds. Simple bases, we'll deprotonate them there to make this carbon minus. Okay? But the part I want to leave you with too, we'll do the actual questions and stuff online, but the part I want to leave you with is because of this, think about it this way. Remember the patty cake we did? There's still 2. Think of them as 2 patty cake systems. The difference now is instead of the triphenylphosphine, think of it as angry, unstabilized carbon minus. Instead of taking this and taking that as the quick, easy step, now it can add like this or add like this. If my carbon nucleophile is more stabilized, it might do this and go, hey, I'm going to try to eliminate. Ooh, that doesn't feel very good. I don't think that's a good thing. You know what? I am going to go back and I'm going to switch. Yes, this is painful. Yes, this is taking calculus for engineers. But man, I got a great job at the end of that. Because the nucleophile is stabilized, it has the ability to take the harder path first to get to the better elimination product, which is then trans. That's why this works. And again, I love doing it now like this because only you guys in class get to see this action. All right, that's where we're going to stop out today. Any other questions before we break on that point, though? Yes, please.
So, just to reiterate,
yes.
the Wittig reaction,
The first, so let me reiterate. The question is, in the Wittig reaction, the first nucleophilic addition is what? Yeah. The stability, or you pick the lowest energy betaine, which determines the only outcome, the higher energy alkene. Yeah, that's right. And here, you could make this one, but you can also make this one, which makes the lower energy elimination product. That's it. Thanks, guys. All right. See you guys on Friday, or Monday. So hey guys, I'm just going to go over quickly the mechanism of the Wittig reaction one more time. So from the arrow pushing side, as we've discussed, we're going to start off with our nucleophilic Wittig reagent, or the nucleophilic ylid. The carbon center here is the one that has the electron density. That's our nucleophilic carbon center. The electrophilic carbon is over here, similar to what we've seen with other cases. We have a nucleophilic attack with those arrows displacing to form this new carbon-carbon bond. So that goes from our, what we called ylid. We call this molecule the betaine. As discussed in class, there's a rotation involved, but we're describing it here where we've just finished this bond. There's then a promotion or formation of an oxygen-carbon bond through space. That's forming this one here. That forms this, what we call the oxophosphate, phosphatane. This is a 4-membered structure. It's think of it as unstable because of ring strain across this, but that's how we're forming this first oxygen-phosphorus bond. Then we undergo the elimination. We're breaking the carbon-phosphorus bond. We are forming the carbon-oxygen double bond. We're breaking this carbon-oxygen bond. So it's a pair of electrons here and here that really is doing that elimination to form the carbon-carbon bond and the carbon-carbon double bond and carbon-oxygen, say that one more time. It's this elimination to form a new carbon-carbon double bond and breaking the carbon-oxygen to make the oxygen-phosphorus double bond when you go through here. As I mentioned, if you look at it overall, it's this displacement of 1, 2 new sigma bonds and 1, 2 new pi bonds altogether. The geometry, as discussed in class, we're going to have an orientation where the dipole across this carbon-oxygen center will align in this direction. Likewise, that dipole is set up here. So aligning those two dipoles together, oxygen-carbon dipole in this direction and carbon-phosphorus dipole in this direction. That's why you get the specific 180-degree approach between these two centers. So seen in the sawhorse projection, the oxygen carbon bond is down like this, and 180 degrees to that is the phosphorus carbon bond here. If we were to look down this bond right here, in Newman projection, you'd see that the phosphorus is up here in front, and then in behind, we're looking down that bonding axis, gives us the oxygen carbon. So once again, those are always in that first intermediate, 180 degrees to each other. Just from an abbreviation point of view, this phi group is how we abbreviate the phenyl, so we don't have to write pH each time potentially. Now, to get to the betaine for elimination, the oxygen is pointing in one way, the phosphorus is pointing in the other way. That's why we have to go through this rotation of this center bond here. And in doing that, we're going to be forming a new oxygen to phosphorus bond. That's how we get this structure here. In the Newman rotation, that rotation there would be seen as you hear over on the right side of the page. We're putting the oxygen and phosphorus close to each other. And the thing to note is now those two R groups are on the same side of the plane made by this carbon-oxygen or carbon-phosphorus system there. That's why they're on that same point. Likewise, they started off opposite each other here because sterically that's the preferred geometry. Then in our final step, once we've made this oxophosphatane, we're going to break the carbon-oxygen bond, and we're going to break the phosphorus carbon bond, forming a new pi bond here and a new oxygen to phosphorus pi bond there. That gives us our final two components here. So that's our final bond geometry manipulation that we've seen. As I mentioned, this is going to be the movie. You can access it here online. That's the movie that is located on Reddit. I'll post this video as well on Canvas. So for this reaction, we're asked to determine the major products of this particular transformation. Now, just as a category here, if you look at the reagents, we're using a triphenylphosphine sort of system, and we are doing an addition with this carbon center. To identify the partners, we have our electrophilic carbon here, that's our carbonyl. As it stands, this reagent here, we're actually missing some charges. So if I were to draw this out as it is, to complete this, if I have this structure drawn here, remember that can sort of be drawn as carbon phosphorus, and we've got our 2 protons over here, and then our 3 phenyl groups. So that's really what I'm describing here in that sort of the formula. The other way to look at this, remember, is as carbon phosphorus like this with my 2 hydrogens. So that's explicitly showing this with my negative charge and my positive charge across these two. So now in this resonance form, it's explicit that it's nucleophilically negative. I'm not saying you have to draw that. I'm just I'm showing you that geometry, which means we're transferring this group here. That's the carbon center that's being transferred. The other constituent components, my oxygen and phosphorus, are the other products from here too. So redrawing this, I would start off with my ketone component, where again my electrophilic center is here. My nucleophilic carbon, this one right here, would be double bonded carbon, and everything that came along with it, not including the phosphorus, that's the payload, would be redrawn. So it's the CH2 in the center. The other products from this, we're going to have our P triphenylphosphine, and that is now going to be triphenylphosphine oxide. Those are the 2 products. There's nothing to worry about here for E and Z geometry because it's symmetric about that center, right? So this is the only product we have to consider. Nice and easy. So for this one, we want to identify the reagents that can be used to produce the following compounds via a Wittig reaction. Now, there's a couple of different ways that you want to do this potentially, because remember, the problem when we look at this in a retrosynthesis way, we have one carbon here, and we have one carbon here. If we're saying it's by a Wittig reaction, you want to focus on this carbon-carbon double bond. That's what we're forming. Now, remember, as we discussed, there's kind of two polarities we could adopt, right? There's either one geometry where the green center here might be my electrophile, which makes this purple center my nucleophile. So let's take it under that case first. Let's assume that the nucleophilic center was here, making the electrophilic center this one. Now, when I say electrophilic center, the possibility is that this molecule would be my electrophile, which means that's my carbonyl component. So that would be this aldehyde, for example. If the other one is my nucleophile, that means my nucleophilic carbon was the pH3 positive negative charge here. So that would be potentially the polarization I have across that one. So again, I'm disconnecting across this bond here and breaking it up that way. Now let's look at the alternate, right? What if we were to switch it and say, as an alternative, let's say now I'm going to do blue and red, where let's say now this side is my nucleophile and this side is my electrophile. Okay, under that geometry, the Wittig is going to be my, I'll draw it out specifically. My Wittig is going to be this aromatic center here and negative charge, pPH3 positive, and the electrophile would be across this one, kind of like that. So in the end, either of these two are possible. You know, if you identify these two structures as potential ways, you could look at it and say, now I could choose which one of the two may be more optimal. And there's a slight favor where this side might be a little easier to make in terms of synthesis. Now, what I mean by that is think about not the carbonyl. In both cases, you've got an aldehyde versus a carbonyl. Yes, aldehydes are more reactive than ketones, but look at it in terms of the ylids that you have to form. Remember, in both cases, how do you form an ylid? These ylids, first of all, you're going to start off with, let's say we're going to start off and make this one here. We will start from the molecule where the center that is going to be attached to the phosphorus, that starts off as like an iodine. And we're going to do two steps, right? First step is we will react with pPH3. Second step, you're going to use a base like LDA, right? So it's a two-step process in order to get to that product. Now there's a little, if you think of the nucleophilic attack, the SN2 reaction you need to do to add that triphenylphosphine, this is a primary center, so that's going to be a little bit easier to carry out relative to the opposite. Over here, the SN2 reaction I would have to do would actually come from this one here. It's a nucleophilic attack at this iodine, which is a secondary center. So that maybe if you were to kind of look at it, SN2 on a secondary center is a little bit harder than SN2 on a primary center. Just as a quick call back to your second year in 123 notes. All right. If you're asked to propose a synthetic pathway to make this molecule using a Wittig, once again, we have sort of those two possible geometries. You could choose, we're going to be breaking this bond, and then one center will be a nucleophile, one center will be electrophile. Using the principles we've marked before, I'm just going to say that the green center will be my nucleophilic center, which means it's going to come from something like pPH3 plus minus, and the other side then is my electrophile, that's my carbonyl, like this. Now, if you're going to be making this from a Grignard type Wittig type reaction, you want to look at the two fragments and see, does the geometry match what we hope or expect. If you go through this, bulky group is this methyl group, at least relative to the hydrogen. So this is our more bulky group on that side. On the opposite side, this cyclopentyl group would be the bulky group compared to the methyl group on this side. So in this case, you can see the two sterically larger groups are on the same side. That would match what we'd expect from a Wittig type reaction in this case. So there's no issues in terms of our starting material choices to get that outcome. So as the last part, we mentioned the Horner-Wadsworth-Emmons system. We'll go through this in more detail at the beginning of next class. But here's a case where my carbon nucleophile, in this case, is now stabilized by resonance. We have pi bonds adjacent to that negative center, which means it can be delocalized in two different ways. One up that way versus one over this way. That stabilization will lower the energy of this nucleophile, allowing that addition to be, I shouldn't really draw it like that.